my friend.
Yeah, today we have a special guest. It's my honor to introduce him. He's not only a distinguished lecturer, but also a graduate of our department, and also a good friend of mine. Dr. Tekin received his BS and master's degrees from this department in 1992. And then he received his PhD degree from Ohio State University, Electroscience Laboratory in 1997. He worked with fluorescent technologies in Bell Laboratories, and since 2000 he's a professor at Sabancı University. His current research interests include RF and microwave circuits, millimeter wave antennas, and circuits.
Welcome. It's nice to be here. Graduated in 1990. I took many courses from Sencer abi with Özlem. And Özlem was my lab partner in third year and fourth year. And then we also collaborated in many projects. Since 2000, I am at Sabancı University and I am doing research on antennas and microwave circuits at different frequencies. Today I'm going to talk about, although Sencer abi have some question marks, full duplex communication. I'll tell you in a minute what this full duplex is all about. Here's a brief outline. There are many different technologies for 5G. So I'm going to give you a picture of what's 5G about, and then what's in-band full duplex. So there are some challenges to be resolved in in-band full duplex. I will give you some of the antennas, microstrip patch antennas with some cancelling circuits, and to obtain this isolation. Since you're in electromagnetics class, maybe you haven't seen like S21, S11, but you have to know these subjects. That's all you're going to use when you graduate, like reflection coefficient, S11, S21, insertion loss, and so on. Then I'm just going to show a few pictures of our university. Okay, so wireless communication is evolving, although when you look at the beginning, it starts in the 1920s, but the commercial deployment started in like 1980s. The Bell Labs is the pioneer in this wireless research. Cellular communications, G stands for generation. The first phones started with analog communication, analog phones, just voice capability. Then 10 years later, a third generation mobile phone system. So the technology, wideband CDMA, CDMA 2000. Now, as you can see, the bit rate is increasing like 30 times, another 30 times. And then here you have some data and then much wider use of these phone technologies. And then the fourth generation, 2010, comes to 100 megabit per second. This is from one cell. It's called LTE, long-term evolution. And then people are now talking about 5G. It's deployed in many places as a pilot networks. They are trying some pilots. But the rates that they want to try, like 10 gigabit per second. So everything is basically, you are going to have internet at very different speeds. And then you have many possibilities. So what 5G is going to resolve? Basically, a continuity in challenging situation. What challenging means? If you're in a high-speed train, or like in a, aircraft, or like fast car, so it has to solve the internet connection, like whether you want to download a movie or watch a movie or listen to a song or chat with your friends. It should be able to resolve this. The second, the 5G was supposed to solve so-called Internet of Things. So now here we have mobile phones, we are reaching internet, but the next, what's being taught, everything will have some internet connection. So maybe you have seen those small Arduino boards, like small computers, lots of sensors, and then they have very small, you can buy $1 wireless LAN connection card. So if you, and then they have like temperature sensor, pressure sensor, and then light sensor. You have lots of distance sensor. You can bring those and then put onto a device, and then that device will report its condition to the internet. So those are called the Internet of Things, the massive number of sensors. So everything, for example, in this room there will be lots of sensor, and then you will be able to reach this data from your network. So that's the second thing, and it should be very high reliability, global coverage, and or very low latency. There won't be a lot of delays. So this, basically, you will have the right infrastructure for this. How are you going to achieve all these things? Basically, I like this flower. This red flower, the yellow flower is like 4G, and then the red flower is 5G. It's like enhancing in many things, like the latencies has to be at 1 millisecond level, mobility 500 kilometers per hour, peak data rate tens of gigabit per second. So user experience data right now, we have like a few megabit per second, so that should be like on the order of gigabit per second. While you're doing this, everything has to be efficient. Spectrum is the one thing that has to be efficient, the frequency that you use. It should be energy efficient, cost efficient. I don't know, I mean, these are wishful things that you want to do. While you're multiplying everything, you want more and more, you want to do it with more efficient scale. So people are talking about different technologies to achieve these, the 5G. What are those technologies? Basically, these are the things they want to increase. These are the technologies. The massive MIMO is one of them. So you put a lot of, right now when you look at base stations, you see a couple antennas, 3 or 6. But with massive MIMO, you will see maybe a phase there, hundreds of antennas. Okay? Ultra-dense network, novel multiple access schemes, the new network architecture, all spectrum access. Maybe you will have this whole spectrum, and you will basically recognize which spectrum is empty, then you will use those frequency chunks. And also, there is a lot of frequency debate. A lot of people say 5G is going to be millimeter wave, but what I see is like, it's like evolving. If you're using for 4G 2 gigahertz, it's not going to jump up to 60 gigahertz, 90 gigahertz. So that jump will not be possible. There will be still some frequency used in the lower frequency, so-called sub-6 gigahertz band. And then there will be frequency at 60 gigahertz, there's 94 gigahertz, because short range communication, but fast data rate will be possible with the use of those frequencies. And one of them is also in-band full duplex. These are key technologies. They are being evaluated. People are trying to find solutions, but we'll see which one of them will be deployed. Okay, I'll just pass this. Internet of Things, everything will be connected to your network, and then you will be reach those things from your mobile phone. It can be your home environment, it could be like security, surveillance, if there's someone trespassing your property. Transportation is a big area for 5G, like car-to-car communication. Right now, when you go into the cars, you have your phone, they have their display, so you can connect with the cars, but there's lots of things you can get from the car. Also, car-to-car communication, road-to-car. So there's a lot of, things to be done in the transportation area. Healthcare is another one. People draw, we will have sensors, basically maybe body-worn sensors, or maybe inserted, will measure our temperature, heart rate, all those vital information, and they are going to be stored. Industry, they call it Industry 4.0, I mean digitalization of the industry. There will be a lot of sensors, and this probably will be connected with big data. And then when you read papers and then you think everything is done, but actually there's a lot of systems to be done. Industry, they are resilient to changes, but you can go with electronic solutions or internet solutions to make them more efficient, you know, to make them more money-making products. I think one of the most important technologies, massive MIMO. As I said, it's going to be a very large antenna array at each base station. Right now, what we have is like a few antennas, and then all users use the same antenna, and then we cannot share they cannot use the same frequency. But if MIMO stands for multiple input, multiple output, massive means you have many of them. In case of massive MIMO, let's say this is you, and then this is the base station. As you can see, there are many antennas. So your information will only be basically transferred to you. Right now it's sent to everybody, which is spectrum inefficient, which is power inefficient. But to be able to do such things, you have to have like complicated antenna systems, and you have to have many antennas, their algorithms. So it's not a very easy job to be able to do this, but people are basically working on this massive MIMO. Two bands, the low frequency band, it's like sub 6 gigahertz, improves spectrum efficiency by special space multiplexing like this. High frequency band, this is at like 60 gigahertz or 38 gigahertz at millimeter wave band. And then there, if you have many antennas, you can you know, coherently add those antenna signals to compensate for the increased path loss, because at higher frequency, the communication distance will be much smaller. Okay, now another technology people are talking is so-called in-band full duplex communication. What's full duplex? You have a transceiver, which means it can transmit and receive, and you have a circulator, and you have an antenna connected, and then you have another transceiver. This can also transmit, receive. Currently, when you say full duplex, this antenna transmits at F1, this system receives at F1 frequency. The other one uses the frequency F2. Okay? Or you can have two transmit and receive antenna, transmit, receive. They can use two different frequencies. When you say in-band full duplex antenna, they will use the same frequency, F1, 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 so that the idea, if you have a spectrum chunk, you can double the amount of data that you send. So if someone uses F1, F1 with the bandwidth, basically it will enable to double the usage of the spectrum. Now, what's limiting right now, why can't we use this? Why can't we use the same frequency? It's just because when you transmit the signal at frequency F1, some of this signal will also go to the receiver. It's just like when I talk to you, I hear my own voice. Okay? When I hear my own voice, I cannot understand what you say. If I somehow cancel my own voice to go into my ear, then when you talk, I will be able to hear your voice. Okay? So in that case, we will be able to talk and listen at the same time. Also, we have to have two brains, I guess, to process when you talk, and then split the brain into two. But for this case, it's easy. You can have a transmitter and receiver. Okay, so that's the problem. And most of the in-band full duplex communication, if you become a microwave or RF engineer, this is another thing you need to know, dBMs. It's called the Decibel Milliwatts. So we always talk about in terms of decibel, because the signal levels, when we transmit 1 watt. When we receive 1 picowatt. The levels are so huge. Instead of talking like 1 picowatt, 1 nanowatt, we convert them into dBs, and then we talk in terms of dBMs. dB, M stands for milliwatt. 25 dBm, that's the transmit power level of a mobile phone. And this is, if you have like some bandwidth 20 megahertz, this is the level minus 85 dBm. Basically, that's your noise floor. So you have to decrease your transmit leakage into your receiver to the noise floor. So you have to decrease the signal level to the noise floor. This is a typical architecture of a transceiver. So this is something called coding, and then you have DAC, digital to analog converter. So this top part is the transmitter part. This bottom part is the receiver part. Most of the time you have some common circuitry like local oscillator, which is both used for the transmitter and the receiver, but most of the time you don't have a relation between transmitter and receiver. Okay? And then they are both connected to the same antenna with a duplexer. What happens if you don't have any cancellation? The transmitted signal comes here, and then from this is called the duplexer or circulator. It goes from the antenna, but some part leaks to the receiver. So we want to cancel this, leakage signal. So what's the idea? You can cancel this signal here, so-called RF front end, radio frequency front end, which has like signals working at RF frequencies like power amplifier, low noise amplifier. So you can do some cancellation in the RF front end, you can do some cancellation on the digital, and then you can do some cancellation if you have the proper antennas, as the amount of cancellation needed is around 100 and 120 dB. So you need to decrease the 1 watt signal level to 1 picowatt, so you have to cancel it. So usually you get 40 dB at the antenna level. 40 dB means 10,000, so you have to decrease your signal to 1 over 10,000. You get 40 dB at the antenna level. At the RF cancellation, you get another 40 dB. At the baseband, you get another 40 dB, so you achieve 120 dB. Okay, so I'll just pass this. So our motivation was, instead of using antenna, RF analog cancellation and baseband cancellation, we wanted to develop antennas such that instead of using this RF analog cancellation circuit, we wanted to obtain this 80 dB, almost 80 dB at the antenna stage. We wanted to develop antennas which can do this 80 dB cancellation. And since we have like 30, 40 dB cancellation at the digital, then they will add up to 110 dB. By the way, even if you have cancelled 90 dB, that your system will still work, but it's going to work with a smaller range. If you do more cancellation, your system will work for a longer range. Okay, so for this, we chose the one of the mostly used antennas, so-called patch antenna, microstrip patch antenna. It's when you know antennas, you know it's not that strange. But if you don't know antenna, it's very strange. So you have this patch, you connect two wires, and then you send a signal from here. It doesn't go to that signal. What would you have wire, right? Signal is from this point to this point. It's not reaching that point. There's a current, but so that's the. You have to look within like antenna engineer's point of view. Otherwise, if you show this to any electrical engineer, there are two metals connecting 2 points. Signal will go from that point to that point, right? With some ohmic loss. But this patch antenna radiates. The antenna radiates. It's not the circuit loss. It's the antenna loss. This will create one polarization. This, if you feed from this port, this will create another polarization, and there will be so-called isolation between these two ports. They will not affect each other, okay? And then they will basically, if you send a signal from this port, it will not go to this port. Our aim was to obtain, again, like 70 dB, 80 dB isolation. We looked at, this is the simple antenna, dual port, dual polarized, means one of the polarization is in this direction, the other one is perpendicular. These are the radiation pattern, how these antennas radiate. And then we have seen the S21, so-called isolation. S12, S21, I guess you haven't taken the microwave, the antenna course yet, but when you take those courses, you will learn S parameters. Basically, S12 means you send the signal from one port, how much that signal goes to the second port. Okay, it's the insertion loss or isolation between them. So S12, basically, when you look at these curves, so we have some parameters, distance, change. So the level that you obtain by, it's like 30, 40 dB. So if you have a simple antenna, two patch connected with two lines, you get like 30 dB isolation between those 2 points. This is we have measured these antennas. It has 50 megahertz bandwidth, which means this antenna works for 2.4 gigahertz. And then this is also S11 of the antenna. That's a measure of, if you have an antenna, you send a signal to the antenna, you want that signal to radiate. You measure how much signal comes back to you. Okay? You send a signal from, for example, first port, and that signal is reflected, is coming back to you. If that's minus 10 dB, means 1/10 of the power is coming back to you, then antenna is said to be working. In that 10 dB bandwidth, again, you can see like the peak isolation is like 40 dB, but most of the time, we are not interested in these peak levels, but we are interested in a bandwidth, how much, for example, if this is 50, antenna is working in a 50 megahertz, in 50 megahertz we get like minus 35 dB isolation. Okay, so this is basically one thing you can obtain from these simple patch antenna. So you want to obtain 70, 80 dB. So this is another version of this antenna. It's fed without touching the antenna. This is sometimes useful because you want these guys to be DC isolated. If you have some DC sensitive RF circuitry, so this, even if you touch the antenna, your static voltage will not reach. So there is no difference between these guys and then the directly fed. So you can obtain like 35, 40 dB isolation. If you put two antennas separately, okay, so this is one antenna, this is another antenna, and then dual polarized, if you feed, you will see again the antenna is working, and then you can obtain like 45 dB basically isolation between them. By making these antennas further away, you can get more isolation, but in that case you will have a very large system. So you don't want to do that. You want to have a large isolation, but you want this in a limited space. Okay, we tried some RF circuitry. So this is the patch antenna, and then we wanted to take some signal from the input port and then cancel. So the idea is you have a signal coming. How would you cancel that signal? If you take the original signal and then adjust its amplitude and then change the phase 180 degrees, so-called feed forward. This is a coupler, and then you take the signal. This is attenuator, adjust the amplitude of the signal. This is phase shifter, adjust the phase of the signal, and add with a coupler to the other port. In that case, you can decrease the level of isolation. Originally here it's like 30, 40 dB. You can decrease that number to like 95 dB. But the bandwidth is important. You can, with this circuit, you can cancel at one point, but you need to cancel in a bandwidth, so that this would be useful. If you just, it's not this peak point or minus 75 dB or 95 dB, but it's what's important, it's this bandwidth. This does not change Of course, if you're going to use your system in like 1 or 2 megahertz bandwidth, then you can have a higher isolation. But if you have like 25 megahertz or 50 megahertz, by adjusting this peak value, your bandwidth gets smaller. So this is no help if you need this canceller for a large bandwidth. Okay, then we wanted to basically look at the antenna, not like an antenna person, but like a just a communication, simple idea. If this is my transmitter, I want to cancel this signal on the receiver. So what I need to do, take 2 samples on the exact same point, symmetric point, and then cancel them, like subtract them, right? So this is a very simple idea. If there is a signal coming to you, if you take 2 samples of that signal and then 180-degree phase difference, then it will cancel. So this is the transmitter, these are the 2 receivers. This is basically red trace, so-called. It just takes 2 signals. It takes 2 signals from here, and then it gives you the difference here, it gives you the sum here. Again, let me make some propaganda of microwave antenna courses. So you will learn how these things work. This is a red trace coupler, okay? So you will learn these in your microwave courses. So we first did the simulations. Again, so you can see this 30, 40 dB isolation level. If you do some circuit like this, the peak value like 90 dB, but the bandwidth goes to like 50, 55 dB. So previously we were obtaining 30, 35 dB, so increased to like 55 dB. We did this antenna, so this is our transmitter, these are receive port, this is the red trace coupler, okay? And then actually, when you build these antennas with the same thing, with the simulations, I mean, we haven't seen like 50, so we have those levels, but in a 50 megahertz bandwidth, so it has like 40 dB isolation, 40 dB isolation between these 2 ports. Sometimes simulations will give you very good results, okay? The way that you simulate, there are many different simulation tools, like there are ADS, HFSS, CSD. Sometimes you want to get some fast results, you do simulations with the easiest one, but they will give you the best results. For example, this previous one. So these are simulated in ADS, and then combined, so you get these results. This one, so it's like full implemented, and it's evaluated in HFSS, then you have like more realistic result. The isolation, when you look at here, it's like 40 dB. Okay. Now, the next thing, we took the receiver feeds to these points. It's interesting, although you feed from the same side, you think that the polarization will be the same, but this guy transmits, since you have like subtraction, this creates opposite polarization. So you have again, this isolation coming from the polarization. Although I feed this patch antenna from the same side, if I feed this the difference port, I will excite the polarization in this direction. Okay, since we realized it's different polarization, why not just directly feed this antenna from the opposite ends like this, okay? And then use again the same difference circuit to obtain. So we get basically the much nicer results, like 80 dB, but like 60 dB in a much wider bandwidth. We get these isolation. This is the antenna. Okay, this port will excite this polarization in this direction. The other one, the orthogonal polarization. And these are S11 showing the antenna independently works. And then when you look at these values, like 60 dB, like 50 megahertz, like more than 60 dB isolation is obtained. So taking these to here, we get like more isolation. Okay. If you have like much larger bandwidth, like this is 100 megahertz, you get 60 dB isolation. At 2.4 gigahertz, you basically need 100 megahertz for wireless LAN that we use. So you definitely get 60 dB isolation. And then, so this is another version again, although they look like touched, so these are like T-step. So this is like around 50 dB. One step, we wanted to do like cancellation in the other one too. So differential, this port is differential. We wanted to make this differential and add another coupler to cancel in both. In simulation, it has like 70 dB, but when we implement it, because of this implementation, you can see this is the measurement, this is the measurement, this color, and then this blue is the simulated. It's like shifted, so it's coming from some inaccuracies and then maybe radiation. These cables, when you measure, they have like 70, 80 dB radiation, although, so it has to be very controlled. So some levels might not be, I mean, it has to be much more controlled experiment. We wanted to try one more step, and it's basically put one of the ports to the top and put a ground plane in between, and then put the other port here to basically, if you have some ground plane between these two ports, okay, so one is directly fed, the other one is like this, and then you can get like 60 dB isolation with this speed. Again, in simulation it's much higher. When you do these antennas, it's like 50, 60 dB. And then the last step we wanted to make, combine those like canceller with the slot. Okay, so I think if you connect from the patch antenna, if you use two ports with with different edges, you get 30 dB. If you cancel with the circuit, you get another 30 dB, and then with the slot, you get another 30 dB. If you do it like very nicely, you will get 90 dB. Cancellation, you cannot cancel two numbers and then get 0. So, like you have like 1.00, a big number. When you do cancellation, you cannot accurately put all those like 9 digits at once and then get very low values. So it has to be like step by step. Like you get, it's just like you know, going down the steps. You have to go 3 steps and then 3 steps and then 3 steps. Okay, so we wanted to combine all those ideas, the differential feeding and a slot, and then from the other edge, ideal difference is like this, so you get 0, 120 dB simulation. If you use a hybrid coupler, if it's like a perfect hybrid coupler, you get like 100 dB. Okay? These are again simulations. But when you implement this, so this is the antenna, from the other side there's a ground plane, and there's a slot which feeds this antenna. This is the red rays. So when you simulate this finite structure, you get like 80 dB, and then like peak 90 dB. But the nice thing, it's a broadband, so it's like 80 dB, like 75 dB for the whole frequency. And this blue is the measured result. So within the antenna frequency, you know, you get like 75, 80 dB easily between these two ports. The antennas, the ports, one of them is here, the other one is here, and then the coupling from this port to this port is like almost like 75, 80 dB. Now, if you use this antenna with these like software-defined radios, you can digitally obtain another 30 dB, and then you will get this total of 110 dB isolation. Okay, so this is probably enough for microstrip patch antennas. I have presented some of the antennas evaluation, and then we basically get 75, 80 dB isolation. And also, we are testing these antennas for it's called the WARP, Wireless Open Access. It's a software-defined radio. It has RF parts, it has FPGA, you can write your codes using MATLAB, and then it will do like whatever you say it to do. We are using that board with these antennas, and then we are implementing these digital cancellation to obtain. So far, we are at the level of like 100 dB. We can obtain cancellation with one of the antennas, and then digital part like 100 dB. So we are very close to obtaining this 110 dB. I just want to show what we have in Sabancı University. You have a larger one. We have an anechoic chamber. It's a spherical positioner. We measure antennas. It's a like 3 by 5 meter room. This works up to 40 gigahertz. And then next to the this basically anechoic chamber, we have so-called to measure. We can measure from 75 to 110 gigahertz W band. So-called one of these 5G frequencies will be 60, 77, 94 gigahertz. So if we have some antennas or RF circuits, we can measure those circuits with the help of harmonic mixers. So this is a very good setup, but it takes long time to adjust and measure at these frequencies. It's very difficult. In addition to these, we have an RF wireless communication lab. Over there we do like antenna measurements, like simple antenna measurements, and then rotational platform, and then we have network and spectrum analysis. I guess this will conclude my talk. Again, it was my pleasure and honor to talk here in front of this great audience. If you have any questions, I will be pleased to answer. Thank you.